So let's take a look at some practice problems for permutations. As always, there will be links to the times of the beginnings of problems in the description. Feel free to skip ahead if you understand the problem. I will present the problem, give you a few seconds to pause the video and solve, present the answer, and then the solution to how we got that answer. So if you understand the problem, skip the solutions, move on to the next problem. Example 1, evaluate each of the following: 10p3, 8p1, 12p12, and 12p0. Feel free to pause the video, evaluate these. You should be able to evaluate all of them without a calculator. This one here may take a long time if you're doing it by hand, but you should be able to do the rest pretty easily without a calculator. So, here are the answers. 10p3, we know that that's going to be the same thing as 10 factorial over 10 minus 3 factorial, which is going to be 10 factorial over 7 factorial. So this is 3 bigger than that, means that this has the extra terms or factors 10 times 9 times 8. So the rest would cancel out. The 7, 6, 5, 4, 3, 2, 1 top and bottom would cancel, and that gives me 720. 8p1, this is just permuting one element out of 8 total, so it's the same as just picking one of the 8. There's only 8 things I could possibly pick out. So using the formula, that's going to be 8 factorial over 8 minus 1 factorial, and I'll show it a little bit more clearly than I showed this one. That's 8 factorial over 7 factorial. Now either you've seen they already cancel, or you can list it out and see they cancel. That's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 7 times 6 times 5. Let me make sure I'm writing times 4 times 3 times 2 times 1. 7 to 1 cancels out. When you cancel out by division, you're left with 1 at the denominator. So we end up getting that equal to 8. This one here, 12p12, is going to be 12 factorial divided by 12 minus 12 factorial. Now, we know that 12 minus 12 is 0, so we end up with a 0 factorial in the denominator. 0 factorial is 1, so this is the same as 12 factorial. And either I can do the work longhand, 12 times 11 times 10. And if you really love multiplying numbers together, you can just give yourself some factorial problems and go to it and have a ball. But I don't love it that much. I would go to the calculator for this. And so either I can use the NPR and type in 12 math NPR 12, and we get, ooh, what'd I mess up? Extra parentheses. That's going to be 479,001,600, or I'll show you it's the same thing as 12 factorial, so 12, same answer. Alright, last thing, now we talked about this in the previous video, if I'm permuting 0 elements, there's only one permutation, it's sort of the one thing that has nothing permuted. I was trying to think of good examples of this, or good metaphors or similes of this later on, earlier today, and the idea is this. So I'm trying to find rearrangements, and if I have 3 cards, we know that there are 3 distinct cards, we know that there are going to be 6 ways to permute all 3 of those: ABC, ACB, BAC, BCA, CAB, CBA. If I have nothing to permute, there's just this one empty thing sitting. It's the same idea as having 0 of something, same idea as having an empty set. They still have meaning even though I'm not permuting anything. I still count that as something going on here. it will be 1, and the formula will show that it's 1. So 12 factorial over 12 minus 0 factorial. 12 minus 0 is 12, so we have 12 factorial over 12 factorial. 12 factorial is this big ugly number, but when you divide something by itself, as long as those things aren't 0, you get 1. Example 2. Evaluate NP3 for all integers n such that n is greater than or equal to 3. Pause the video. Feel free to solve this. Okay. Answer should be, when expanded out, n cubed minus 3n squared plus 2n. And here's how we get to this. So NP3 we know is going to be n factorial divided by n minus 3 factorial. And no matter how you look at this, either you do this the way that I showed earlier in the factorial lesson, where this has 3 more terms than this, because n is 3 bigger than n minus 3, and those terms are n, n minus 1, and n minus 2, and then we would still have n minus 3 multiplied all the way down to 1. And you can see here, then minus 3 factorials will cancel. Cancel, cancel. And now I just need to evaluate this out. So the way I would usually do this is I'd multiply these together first, and you would get, whether you double distribute, FOIL, area model, whatever the heck you do. I'll put up some videos about multiplying binomials together, but n squared minus 2n minus 1n plus 2, and we still have this n out front. And combining like terms, we got n squared minus 3n plus 2. Distributing through the n, we get n cubed minus 3n squared plus 2n. All right, example 3. In the Wimbledon tennis tournament, the men's singles tournament starts with 128 players. In how many ways can there be a champion and a runner-up? Pause the video. Feel free to solve this problem. All right, there are 16,256 ways to get a champion and runner-up. The idea is this: champion and runner-up are 2 distinct things, not the same, so there's order to them. I just do 128 P2. If I'm doing that by hand, that's nice to remember that it's going to just end up being 128 times 127, because I have these 2 spots, 128 possible first place, and then once I have one person for first, 127 possible second places. I could use the formula, 128 factorial over 128 minus 2 factorial. And any way I do this, I should end up with 16,256. Now, let me look into the calculator. There might be an issue with this numerator, and I want, at least for the TI-83 I'm using here. But the 128P2 should still work. So 128 go over to P2, and I got that fine. However, let me type this in and see if something goes wrong. I think it should, because this should be a large enough number. And I'll explain what's happened there. It's 128 factorial divided by, and that's going to be 126 factorial. Yeah. So what happened here, error overflow. The calculator can only hold so many significant figures. It, when those get extremely large or extremely small, it will switch over to scientific notation. It's a floating point type variable. So it'll keep track of significant figures and then powers of 10. And so if I did something relatively large, like let's say 20 factorial, it's fine. You know, it says this is about 2.43 times 10 to the 18th. So I guess 19 digits before the decimal place. So I guess there will be nothing after it, a 19-digit number. But the calculator only allows for a certain power of 10 over here. And once we surpass that, the calculator can no longer store those numbers. And instead of sort of carrying over and getting to a wrong value, it just says overflow. We have overflowed the bounds of the number. So be careful when you're doing these. If you just sort of try typing this in, it gives you an overflow error. That means something got too large. You know more. You know this is just going to be 128 times 127. So if you get that overflow error and you don't have a calculator that's doing it correctly, try to do some thought beforehand, reduce things down a little bit, and you can still get the correct answer. Okay, example 4. In how many ways can you permute the letters in pre-calculus? Pause the video, try to solve it. Alright, there are 4,989,600 ways to permute those letters. This is very similar to the Mississippi example in the main video. So we can see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. So 11 factorial. But in here, there are a couple of repeats. So P is only here once. I could put a 1 factorial. It's not going to change anything, so I'm not going to put it. R is only repeated once. E is only repeated once. But C is repeated 2 times. So I'm going to have a 2 factorial down there. A only shows up once. L is repeated 2 times, so I have a 2 factorial for that. I've already counted both of the C's. U is repeated 2 times. So now I've taken care of the P, R, E, the C's, the A, the L's, the U's, and S only shows up 1 time. Again, I could put a 1 factorial. It doesn't change things, so I just have this 11 factorial over 2 factorial, 2 factorial, 2 factorial. As a reminder, 2 factorial, 2 factorial, 2 factorial isn't 8 factorial. It should be pretty clear when you start actually multiplying through. You're not getting to 8 times 7 times 6, that garbage here. I'm not going to list this all the way out. It's 11 times 10 times ellipsis times 2 times 1. I just put in the calculator. If you don't have a calculator, it's doable. But when you do all this work, you will get the 4,989,600. Alright, example 5. In how many ways can you make a license plate with 3 letters followed by 4 numbers? And you are allowed to reuse letters and numbers in this one, and you are not allowed to reuse letters and numbers in this one. Pause the video, solve these problems. Okay, so I've seen these problems show up a lot on tests from teachers, maybe a little bit on some type of standardized test. Here are the solutions. And here's how it works. For the first problem, this actually goes back to, you know, high school. You might even see something like this in a junior high level class, where we have 3 letters. Don't ask me why I used the word 3 here, but the number 4, I just realized that, followed by 4 numbers. Now, if I'm allowed to reuse letters and numbers, well, there are 10 digits, and that's worth noting. A lot of people say, okay, a digit, well, it goes up to 9, so there should be 9 of them. Well, the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and there are 10 of these. Digits deals with 10. So I have 10 choices for the first, wait a second, those are letters. 10 choices for the first digit, 10 choices for the second digit, 10 choices for the third digit, 10 choices for the fourth digit. For the letters, if I'm considering a standard English alphabet, then we have 26 letters, and if I'm allowed to reuse them, then I have 26 choices for the first letter, 26 choices for the second letter, 26 choices for the third letter. And when I multiply all these together, I'll get 26 cubed times 10 to the fourth, which is actually probably sort of the preferred way I would look at this number. It has a lot more meaning to it. Multiplied through, you will get this. And this includes, this is how we count up the number of elements starting from sort of the first license plate, A 0 0 0 0, all the way up to the last license plate, which would be ZZZ 9999. I should have some type of order to these things. If I'm not allowed to reuse the numbers, then I have to do something a little bit differently. So I can still set up the same way and avoid using our formulas, and I'll do that first. So if for this first letter, I have the choice of any of my 26 letters. But once I've chosen a letter, I only have 25 remaining. And once I've chosen 2 letters, I only have 24 remaining. And this right here is 26p3. 26 letters, I'm permuting 3 of them. The digits here, if I've not used any digits yet, I have 10 choices, 0 through 9. And once I've chosen one, I have 9, 8, and 7 remaining. And this is the same thing as 10p4. And way back to the sort of intro, the basics of counting, since I'm doing this and then this, I multiply. And same thing as just sort of multiplying all this stuff through. And when I end up multiplying all of this, I will end up with 78,624,000. Okay, last example. You have 2 English books, 3 science books, and 5 math books from your various courses in college. In how many ways can you put these books on a shelf, given that all the English books need to be together, all the science books need to be together, and all the math books need to be together? So, take a few minutes, pause the video, solve the problem. Alright, there are 8,640 ways to order these. Now, just clarification, there are 2 English books, but they are different books. There are 3 science books, but they are different science books. 5 math books, but they are different math books. So here's the idea. I want to group these all together. I want to group these together, group these together, and group these together. So really, I'm trying to permute 3 groups of books. That's 3 factorial. So this is to permute the groups, which is going to be 6. 3 times 2 times 1. Because I could go English, science, math, English, math. Let's see. Science, math, English. I did this in a dumb way. English, math, science, and then math, English, science, math, science, English. I think I got them all there, but I dove right in before thinking, and that's what happens. Okay. Now, the next part, that's grouping up the books, but then if I'm going in the order English, then science, then math, I still have a lot of ways to organize each of the books in there. So since there are 2 English books, I have 2 factorial ways to deal with the English books. Because there are 2 of those. It can go book A, book B, or book B, book A. Since there are 3 science books, I have 3 factorial ways to deal with the science books. And since there are 5 math books, I have 5 factorial ways to deal with the math books. And this is actually very doable by hand because we know each of those factorials already. So 3 factorial is 6. 2 factorial is 2. 3 factorial is 6. 5 factorial is 120. And when I multiply this all together, I can do 6 times 2 is 12. Times 6 is 72. Times 120, well, 72 times 100 is 7,200. 72 times 20 gives me let's see, that's going to give me 1,440. And when I do add those up together, I get 8,640. Possible ways to arrange all of them. Deciding which book comes first, ordering English books, ordering science books, ordering math books. Alright, feel free to put comments with any questions you have. I'll try to continue getting these up. And if you do have additional things you'd like me to try to cover, feel free to comment on that as well. I'll get to as much stuff as I can, as soon as I can. But yeah, feel free to comment on that.